This is Rifat Bari, Master's in Physics student at Brown University, an Ivy League.
Hi everyone, my name is Suborno. I'm pursuing my bachelor's in math and physics at New York University. So Einstein invented special and general relativity. Well, special relativity in specific, he came up with the notion of it using the mathematics of Minkowski and Lorentz in order to build on that in one of his 4 annus mirabilis papers.
And the idea of general relativity has given us some of the most profound things in the universe. For example, black holes, white holes, wormholes, the idea of an expanding universe. Everything that we research in astronomy right now comes from general relativity.
Of course. So, what is general relativity? Well, at its core, general relativity is just a theorem that states a theory of gravity that states that essentially what's happening in the universe we can wait. No, please. Let me finish. We can express it as essentially a coordinate system or scalar field of the amount of mass at every point in space, and that amount of mass bends space-time in order to create the phenomenon known as gravity. And that's what we call the stress-energy tensor.
And today we're going to show you the difference between our old idea of gravity, the Newtonian picture of gravity, and Einstein's theory of gravity. And we're going to give you a taste of special relativity, which is general relativity at the very, very small scales, at a small patch of space and time where there's no gravitational field. Okay, so let's jump in. So let's start with the Newtonian theory of gravity, which was our first model of gravity, right? So Newton ascribed a cause and effect to gravity. A cause would be, for example, an object with a certain mass, and the effect would be that object attracts other objects with masses around it.
Should we draw something or?
No, first I'm just going to write down cause and effect. Cause and effect. So first, what is the equation that describes the Newtonian version of the cause?
Well, of course, given that we have two massive bodies, M1 and M2, such that there's some distance, and by the way, this is just for clarity, M1 doesn't necessarily need to be smaller than M2, nor the other way around. So, if the distance between their centers is R, and they have masses M1 and M2, then we get the formula, the force of gravity between them, which is not an action-reaction pair, they're being pulled together like this. So you get G, which is a gravitational constant discovered by, I believe, Henry Cavendish, times M1 times M2 divided by the radius squared.
Perfect. Great. This is the cause of gravity in Newtonian mechanics, right? And now let's write down the effect. Okay, the effect. So you have two objects, they pull each other with some certain gravitational force, and that pull results in an acceleration. Oops. Right? So let me...
It's okay. You have a marker.
No, okay, sure. Let me write down the acceleration, which comes in the form of Newton's second law, right? F equals?
Ma.
Okay, so this is the Newtonian picture. Okay, here is our cause and effect. Now let's write down the same cause and effect in the general relativistic picture. Okay, so in the relativistic picture, what
can you give a reason why Newtonian, why sometimes you have to use GR rather than Newtonian?
I mean, on the larger scales, like for example, the precession of the orbit of Mercury was found to be slightly inaccurate using.
But also, GR has many predictions that Newton could never come up with. For example, black hole.
All right, so this is Newtonian mechanics, and they said that when you have to use the Newtonian mechanics, the small mass, you have to use GR. Why you cannot use F equal ma, or rather G m1 m2 over r squared, which is Newtonian universal law of gravity?
Okay, so to answer that question, it's a very good question. Let me answer the question with a very small diagram. On the x-axis, I'm going to write speed. Okay. On the y-axis, I'm going to write time. And on the z-axis or y-axis, I'll write size. If things are going very fast, at a very fast speed, we need special relativity, right? Special relativity. If we have something that's very small in size, do you know what we need?
General relativity.
Quantum. mechanics.
Oh, so like
Okay.
quarks, for example.
That's right. And if we have something that is very massive, instead of writing time, let me write mass. Okay. If we have things that are very massive, so we can't ignore gravitational effects, then what do we need?
General relativity.
General relativity. So only our intuition, this is you standing right here, our human intuition, which was tuned in the forests of the African jungle, they're tuned for low speed, low mass, medium size objects.
Yep,
Okay?
and that's why once you approach this from all three directions, you get Newtonian mechanics.
This is the arena where Newton's equations hold. Okay, so if you want to, what does that mean in terms of physics? In terms of physics, that means if you have objects with a low mass, as m approaches not zero, but as m becomes smaller, you should approach Newtonian mechanics. As v approaches much smaller than c, if v is much smaller than c, you should approach Newtonian mechanics. And if h goes to zero, h is Planck's constant, then you should go to Newtonian mechanics. Okay, so that tells you when you should use these three fundamental theories of nature. So high speed, special relativity. If your speed is much less than the speed of light, Newtonian mechanics. High mass, you use GR. If your mass is not too big, you can use Newton's laws. If you're very small, then you have to use quantum. But as h, Planck's constant, approaches zero, you can use Newton's equation. So that's the idea.
Very nice.
Relativistic picture, okay?
Mhm.
So that is going to come in the form of Einstein's equation. Do you remember that, or you want me to write it down? Okay, let's write it down. So you have R mu nu, R.
Hey, what does mu mean?
Well, right now the purpose is not to understand this, it's just to show the difference.
Okay.
Physical difference.
Okay, just 1 second, guys. All right, so there are these little funny things in linear algebra that we call matrices. And these indices are meant to index matrices. And yes, I know, they're called second-order tensors, but they basically act like matrices for the purpose of relativity. So that's what I'm going to treat them as. So, for example, if we have this is R, then R11 is going to be equal to 1, because this is 1 and this is 1, this is 2, this is 2, and R22 is going to be 4, R12 is going to be 2, and R21 is going to be 3. And then you're going to see a bunch of these indices sprinkled around everywhere, so I advise you get familiar with Einstein notation, which basically states that if you have yes, the summation convention.
Indices are summed over.
Blah blah blah. Yes, if you have one index upstairs and the same index downstairs, then we're summing over that indice. But adding in 3 sigmas to your equation doesn't look nice, so we just put the convention there.
Okay, great. Thank you for explaining what this mu nu notation means. Okay, so let me just write down Einstein's equation. I'm not going to really explain it, just show what the cause and effect is. This is 8 pi g times tensor t mu nu. So what we have here is the curvature of space and time.
You can also tell the people what the space tells the.
Oh, space tells
Michio Kaku type explanation.
Matter tells space how to bend, and mass tells space how to bend, and space tells matter how to move. Okay, and that's exactly what we have here. This is the energy. Suborno, do you know what the T is? What?
Oh yeah, that's the stress energy tensor,
what does that mean?
Which is essentially just it's kind of hard to explain, but it's essentially just a graphic of all of the mass and energy that's distributed throughout our universe.
Right. So this is the cause, okay? This Einstein basically tells us that the curvature of space and time is directly related to the mass of an object. So space and time is like a fabric. It's like a bed sheet that curves under the gravitational influence of an object.
This is helpful to imagine for a 2-dimensional world, but keep in mind that space-time in our world is actually 4-dimensional. So we don't really have the model of you've probably seen that weird bed sheet model where they have like the sun over here, then the planets orbiting around that. That would be inaccurate because it's trying to simulate a 3-dimensional universe with 2D space-time, but it's a pretty cool visual.
Yeah, that's the cause. Now let me write down the effect. Do you remember the Christoffel symbols?
Yep.
Okay.
I don't
so-
think we're gonna explain them today.
No, well, I'm just going to write it down so the viewer sees that just like in Newtonian mechanics, where you have a cause given by the gravitational universal law of gravity, you have a cause in GR, and the effect is the acceleration. I'm going to write down the same effect here just to show the viewer that the idea is very similar. Okay.
So
Do you?
I'm so happy that you're teaching this course. No, I really mean it. In on the internet, there are not many people teaching the way you do.
Thank you.
Sean
Yeah.
Carroll.
No, both of you, I guess.
All right. So right now I'm not here to explain. In fact, I don't fully understand what this means. But
I do.
okay, you want to explain?
No.
Okay. So just like in Newtonian Newtonian mechanics, we have a cause for gravity.
Newtonian
In
relativity.
GR, we have a cause for gravity here, where the curvature of space and time is directly related to the mass of an object.
And the sad thing is that classical mechanics isn't even actually called Newtonian relativity. It's called Galilean relativity.
That's right. And the effect here is that the gravitational force gives rise to an acceleration. The gravitational force it results in a curvature in space and time. Okay, that's the first big idea. Now we're going to move on into space and time. Okay, so let me erase this. Now we're going to move on to the second part of the.
Very nice.
That was
This
him.
is probably the happiest recording I have ever done.
Sleepiest.
No, happiest.
And you grabbed the chair as soon as you said, "I'm so happy." I think
Can you be tired and happy at the same time?
yes.
Okay, there you go.
What if you finished like 5 homework assignments and now you're like really happy but also really tired? And also, I accidentally erased part of our title, so let's just pair it.
Okay, good. So the second part of the lecture is going to be devoted to the geometric difference between Newtonian mechanics and special relativity. Okay, special relativity is the theory of GR at a very small scale where gravity can be neglected. So let's take a look first at the Newtonian picture of gravity or space-time. Okay, ready?
All right, so
not quite. So what I'm going to draw is the world line of a particle. So first,
what's a world line?
A world line is the path taken by a particle through space and time. So let me explain what I mean.
Okay, can I first just set up what we're going to be doing this with? So when we're talking about relativity in general, we find it useful to draw what's known as a Minkowski diagram. So this diagram is essentially, it's just your regular x versus time graph. So this is just time. If you're using natural units, you can erase this factor. And this is just the position. Now, of course, this is only true for a one-dimensional universe, but let's imagine what would happen. Let's say we have a choo-choo train over here. I don't know how to draw a train, so let's just draw a skateboard. No, I'm just kidding. This is not CCNY. So
No, skateboard you did it in Dr. Kumar.
yeah. So
Limon College.
let's see if I
Is it
can.
going at 20 miles per hour?
Oh my goodness. Or did Mr. Berry break the law? Okay. I'm going to see if I actually have the skills to draw one now. Yeah, I think that's pretty good. So this is a bicycle, for example, and it's moving. So let's say that at t equals 0, it's at x equals 0. At t equals 1, it's at x equals 1. And this is just an introduction to how to use the Minkowski diagram. Nothing relativistic yet. So then what we draw this as is 0. Wait, no. This is 0, 1, and 2. And so basically, think of the state of your system at some point in time and just taking the cross section at that specific point. So, and this would be 1 and this would be 2. So yeah, just like your normal XVT diagram but flipped.
Great. Okay. That's a very nice introduction to this idea of space-time diagram.
And this is a world line.
That's right. Let me give another introduction. Let's say you have a man who is just standing. Is this man moving in space?
No. But he is moving in time.
Why?
Because, I mean, he can't just pause time. He's sitting there for some length of
he's gonna
time.
go older, right?
Yeah.
Even if he's just standing here, he's not moving in space. He's just standing, but he's gonna get older, right? Every second he's gonna move 1 second forward in time, right?
Into his death.
That's right. How can I represent that as in terms of his space-time diagram?
Well, yeah, that's an exercise for the listener. No, I'm just kidding.
No, I'm gonna put CT. This is not natural units. CT.
Oh, screw you. Okay, so anyway, since he's just standing, we're not going to have any perturbations on the x-axis. So imagine, oh my gosh. So imagine at t equals 0, he's standing at some point on the x-axis. T equals 1, he's standing at the same point. T equals 2, he's standing at the same point. So on and so forth. Remember, we're like taking a cross-section of our line to get the state in time. So here we go. This is the space-time diagram.
So if someone is just standing somewhere, they're not moving, then they're just moving in time, but they're staying in the same place in space. Does that make sense?
Why are you asking me?
Well, I mean, you're part of the viewership. So
I know general relativity, Rifat.
Okay.
You haven't even read the full textbook.
Now, let's say someone starts running.
I can draw.
This is not a drawing competition. Right?
Yes, it is. And okay.
Oh wow. Okay. That's nice.
Uh.
Okay, it's not a drawing competition. That's fine. So let's say you have
bicycle.
Let's say you have someone moving forward at a constant velocity. Okay. Then what will their world line look like?
Okay.
A person running at constant velocity.
Well, let's think about it once again. Well, this choo-choo train.
You don't have to do the choo-choo train thing. Just draw the.
Yeah, this was the same thing, but.
Very good, right? It's just a line with a constant slope. That's it. And now this one might be a little tricky for you. Maybe you don't know.
Rifat, I know this.
Okay. Let's say you have, this was man at rest.
Are you going to put accelerating?
Constant velocity. What do you think I'm going to put next?
Acceleration.
That's right. A man who's accelerating.
That's not running. That's being cradled by your mom.
Do you know what their world line looks like?
Well, let's think about it once. Shut! Okay. Well, let's think about it once again. So, that means that we're not just doing constant steps in space.
This is going to be the best GR video in the world.
Yeah, Dad. Thanks for the commentary. We didn't, I love the commentary. So here's what it will look like.
Okay, so that's close actually, but not quite. If someone is accelerating in Newtonian mechanics, what does their dt curve look like if someone is accelerating?
Wait. Oh yeah, that's right.
Yeah.
Sorry. Like this.
What shape is that?
That's a parabola. Isn't this not a parabola?
Are we allowed to have a parabola in special relativity? Because what is the speed limit of the universe?
C,
the speed of light, right? Can anything go faster than the speed of light?
No.
How do we represent the speed of light on a space-time diagram?
Well, wait a second.
We represent the speed of light as a 45-degree line. Notice that nothing exceeds this 45-degree line, not even this guy.
But any parabola is guaranteed to intersect a linear line.
So instead of a parabola, what should it be?
A hyperbola.
A hyperbola. So not something like this. First, let me draw the speed of light. This is the speed of light. Okay?
Well, it's a very similar shape. It's something like this. So,
no.
It's not as curved.
Let me draw it.
Okay. Oh, really? It's not that good?
It will get infinitesimally close. Let's say short here. It'll be like this. This is the hyperbola.
Yeah, but this diagram,
you can draw it from
pretty
there.
Pretty good too, right?
Okay.
Yeah.
So it gets infinitesimally close to the speed of light, but never gets there. So that's an introduction to space-time diagrams. Now we can compare Newton's picture of space and time with Einstein's picture of space and time. Okay, so let me erase the picture we have here. Before I do, let me summarize. If someone is standing at rest, they're moving in time, but are they moving in space?
Nope.
No. What is the speed limit?
C.
If
Speed of light.
someone is moving at a constant velocity, then they're moving in both space and time. So they have a straight line like this. And if someone is going at a constant acceleration, then they have not a parabola, because a parabola would exceed the speed of
A light.
So what do you have instead?
A hyperbola.
A hyperbola.
So it's something that's bounded by two lines.
That's right.
So you probably recognize it from high school geometry as something like this. Sorry, it's a little bit messy because I'm not using different colors, but pretty accurate, right?
And do you know the equation for a hyperbola?
Well, the easiest one is x squared minus y squared equals 1. Or another one that you might recognize is just the classic y equals 1 over x, which is a hyperbola that is uniquely bound by the x-axis and the y-axis.
Now take this equation for a hyperbola.
Mm-hmm.
What is my x-axis here?
Well, let's
what? The x-axis is just x, right?
Yeah, just
not a trick question. Don't worry. This is just x, right?
Mm-hmm.
Okay. What is my y-axis here?
CT.
Okay. Not a trick question, right?
No.
Okay. And I'm going to say, instead of this being 1, I'm going to define this to be equal to something called
the space-time interval.
Is one of the biggest ideas in special relativity. This is just a hint. I'm not going to explain it yet, but now you should see where it comes from.
Why do we need the space-time interval?
We'll get into it in the next.
No, just say. Just say.
The space-time interval is what stays invariant between changes in inertial frames of reference.
Good.
Special relativity.
So why do we wait 1 second.
But
just chill with me here. Okay? Just chill, man.
Okay. I know how to chill.
You're kind of wrong, man. You should get a degree in education first. So anyway, here we need something invariant. Let's think about Newtonian mechanics for a second. So, for example, velocity works the same way in two reference frames. Acceleration works the same way in two different reference frames. Force works the same way in two different reference frames. Voltage works the same way in two different reference frames. So, essentially, what we want is when we have two different reference frames in space and time, which drastically changes our methods of boosting to different reference frames. Think in the next video, right? Transformations between two reference frames in Newtonian mechanics. So, what we want is for the laws of physics to stay the same in every single reference frame, as has been observed by the environment. This is called the equivalence principle. I'm too lazy to write the whole word equivalence.
No, that's the principle of relativity.
Oh yeah,
equivalence principle is that a gravitational field is indistinguishable from an acceleration.
Oops, yeah, sorry. This is the principle of relativity, and it's one of the two axioms of relativity.
That's why I'm here.
Yeah, to correct me whenever I give you guys misinformation.
Okay, good?
Yep.
That's your explanation? Okay, good. So now we are ready to see the difference between the Newtonian picture of space and time and the Einsteinian relativistic picture of space and time. So let me sketch out the difference. So in Newton's picture of space and time, here is what we have. We explained the concept of a whirl line. Can you explain what a whirl line is again?
Well, once again, it's essentially just a track of an object's path through space and time. So, for example, this is the path of an accelerating body. Suppose you hyperbola, sorry. You can run like this. So this is the path of an accelerating body, for example. Keeps accelerating, so at constant unit time.
Yeah, that was okay. We got it. We got
Sorry,
it.
yeah. So that's a whirl line.
That's a whirl line, right? This is the path of an object through space and time, right?
Mm-hmm.
In Newton's picture of space and time versus Einstein's picture of space and time, I think we're gonna compare that.
Mm-hmm.
Okay, ready?
Yep.
Are you ready to compare that?
Mm-hmm.
Okay, let's see. Let's say you have a ball or a person or a car, and it's moving through space and time. Okay, so this is somehow moving through space and time, right? This
Yeah.
is just a ball or a car or something, right?
Mm-hmm.
Moving through space and time, right?
Yep.
Newton tells us that at any given point in time, we can slice space. We can slice all of space at a single moment in time.
Yep.
So time goes up the y-axis.
That's essentially the whole cross-section
Okay.
thing we talked about.
And all of space is contained in this slice of time.
Mm-hmm.
Okay?
Seems intuitive enough.
What Newton is telling us is that, let's say that there are two events. Okay, I'm going to call this
Event A.
2. Okay, and let's say I slice space again over here. Let's say I slice space over here. I'm going to call this event 1.
Yeah.
Maybe here someone releases a firecracker. Do you know what a firecracker is?
No. Yeah,
It's like
just kidding. I know
the
what
4th
it
of
is.
July. Maybe here someone.
That's a firework.
Okay, who knows? And maybe here someone turns on a flashlight. Okay?
Yeah. So
events. Okay?
yeah, the thing is, in Newtonian mechanics, there is no possible way that anyone could observe these two things at the same time. So an observer here.
No.
What?
Yeah, that's the idea. Yeah, that's the idea. Yep.
Yeah. So there's no possible way that there's just one objective time for the whole universe in Newtonian mechanics.
There is a universal time. Everyone agrees what time it is. Someone here in New York will agree with what the time is with the alien in Mars. Okay. There's a grand universal clock. Everyone agrees that event 2 happened after
event 1.
Or event 1 happened before
event 2.
What we call this is that this is called simultaneity.
Yep. And right now we're going to talk about the relativity of simultaneity.
Okay. So there is no ambiguity about which event happened first. Which one happened first?
I think it was probably event 1.
That's right. Right, in the Newtonian picture, the firecracker blew up before someone turned on a flashlight. Okay?
Mm-hmm.
Now let's move on to the Einsteinian picture, the relativistic picture of space and time. Okay?
Mm-hmm.
In the Newtonian picture, here is space at a cross section at a single moment in time. Now let's look at the Einstein's picture. Einstein tells us that, again, let me draw the man or the car.
Yeah, it was a car.
Okay.
No, it was actually an alligator.
Okay, moving through space and time.
Mm-hmm.
But now check it out. In Newton's picture, what's happening? Is there any question about which one happened first, E1 or E2?
No.
No, everyone agrees that E2 happened after E1, right?
Yeah, whichever is the lowest on the time diagram is the one that happened first.
Yeah, everyone agrees, right?
Yeah. That's not the case with Einstein.
But in Newton's picture, take a look. From event 2, where can the ball go? Can it go here? Can it go here? Can it go here? Can it go any way it wants, right?
Yeah.
With any speed, right?
Yeah.
There is no speed limit. Is there any speed limit in Newton's picture?
No, how would he know?
No. The ball can go any direction at any speed, right?
Yeah.
Now let's go to Einstein's picture. Okay? Now we no longer think of a universal clock. Okay, you're blocking the chart. Okay? We no longer think of a universal clock. Instead, at a certain point in space, say there's an event, right? Like a firecracker exploding. Okay, now what we can do is we can define a light cone.
Yup.
This is a light cone, okay? And the light cone tells us that the particle cannot move faster than light. So for example, can it go here?
Nope.
No, it's going outside the light cone, right?
Mm-hmm.
But can the particle go here?
Yeah.
It's still inside, right? Can it go here?
Mm-hmm.
That's right. So that's the idea in Einstein's picture of space and time. At every event in space and time, we can define a light cone that tells us where the particle can go.
Yeah.
Right? And so that's the Einstein's picture of space and time. Now let's take a bit deeper look at this light cone. Okay, our space-time diagram, right? What is the speed limit of the
Well,
unit?
c, and that can be expressed by these two lines.
That's right. That's right. Now, these lines are diagonal, right?
Mm-hmm.
Here I drew only the x-axis.
Yeah.
If I now add another,
Yup. So now we're
axis,
dealing with a two-dimensional universe.
now we rotate these diagonal lines and they become a cone.
If we were dealing with a 3D universe, we'd need a hypercone. But I think this is good for now.
This is a cone, and this is called a light cone because the diagonals of this cone are made of
Light.
beams of light that pass through this event. Okay, and now let's analyze the parts of the light cone. So here is a light cone. Here's the light cone, right? Okay, another event inside the light cone. This is called
Time light.
That's right.
While anything outside the light cone is called space-like.
That's right. Time-like events have a negative space-time interval.
Wouldn't that mean it was complex?
No, because this is the square. We never square root the space-time interval.
But how is the square of something negative?
Oh, good question. Because the space-time interval is defined as minus ct squared.
Understood.
Plus x squared. This should be delta x.
Got it.
That's the idea.
So it is complex.
So space-like, we have space-time interval is positive. And finally, for light-like intervals, what is the space-time interval?
Equal to 0.
That's right. So these are null space-time intervals.
Yep.
Okay?
Yeah.
So, and by the way, the last thing I'll mention is that this is the present, this is the
Past,
future,
sorry.
and this is the past. So this is the future, and this is the present. Okay, so that means if you want to travel to the past, if you want to time travel, you have to go faster than the speed of light to actually influence the past. That's one way that you can time travel. So,
if you liked my teaching, please leave a comment down below.
And folks, if you enjoyed my teaching, please leave a comment down below.